In this video, we're going to look at the reflection property of parabolas. Specifically, we're looking at parabolas through a conic sections lens. And as you can see in this picture, the focus has a really cool property, and that is that if you sketch a line from the focus to any point on the parabola, the angle, imagine it's light, for example, right? Imagine this is a light bulb. So you've got a ray of light coming from that focus to here. Now there's a geometric property that says the angle at which light bounces onto a mirror, it will bounce off at that same angle. So that angle will equal that angle. And one of the cool features of parabolas is that it forces all of the light, let's say, to bounce off in a direct forward direction, right? So this, because this angle equals that angle, right? This is how headlights make all of your light shine forward on your car to illuminate the roadway before you. So anyways, they have this really nice reflection property that everything goes out forward, and also satellites are built on that same concept, right? Those are actually three-dimensional paraboloids, but we're going to look at the one-dimensional slice of them through the center in this video. So we're going to do two examples. Our first one involves a searchlight. So let's say we have a searchlight with a parabolic reflector, and it forms a bowl which is 12 inches wide from rim to rim and is 8 inches deep as shown below. So if the filament of the bulb is located at the focus, how far from the vertex of the reflector is it? Right? So where do we want to put the bulb to make the light shine in the correct direction, right? So what we're going to do is we'll just sketch a little XY axis. I think will help to kind of illuminate the way here. Okay, so we're just going to take a slice of it and turn this three-dimensional problem into a one-dimensional problem. So we're going to introduce a coordinate system where we place the vertex, the bottom of the bulb, the vertex of the bowl right there at the origin. You could shift it, but why, right? That would just make it unnecessarily more complex. And we can just do kind of a rough sketch here of a parabola that is the bowl. Okay, and we're gonna find some points on this parabola based off of the problem as given, right? It says it is 12 inches wide from rim to rim. So at some point we have the rim of the bowl. Let's call it this point right here, right? So that distance in total is equal to 12 inches, 12 inches, right? And we also know that at that same point, it's 8 inches deep. Okay, so coming straight down here, if this is at an x-coordinate of 0, that's at an x-coordinate of 8, right? And this is at I'm sorry, that's at a y-coordinate of 8, because that's 8 inches deep. That's 8 right there. This is 8. Okay, that distance, let me replace that. That distance from the x-axis to there, that's the height of the bowl, in other words, is 8. So even though I have drawn it as if the parabola continues on, right, the bowl stops at the red line. Okay, but we can also find that horizontal distance, right? Because if the total distance across the bowl is 12, and we know it's symmetric, then half of that distance is 6. So that gives us a point that would be on the equation of the parabola that would model the shape of the bowl through the origin, right, is 6 comma 8. Okay, so we know that in standard form, this equation is x squared is equal to 4py, and we're using x squared equals 4py because it opens up as opposed to y squared equals 4px, which would open to the right or left. All right, so now we know a point on that. We need a point so we can solve for p, because if the goal is to find how far from the vertex of the reflector is it being the light bulb, right? So meaning right there, what is that? What is that focus? Well, we already know that the distance from the focus to the vertex is p. So the goal here is to find p. We want p. Well, how are we going to find p? We're going to write an equation of the line, plug in a point, and solve for p. So I'm going to plug in 6 for x right here. Any point on the line would do, but that's the one that would be simplest here because we can calculate 6, 8 based on the description of the bowl given. So when x is 6, y is equal to 8. So what we're going to do is solve that for p. So 6 squared is 36. 4 times 8 is 32. So we get 36 is equal to 32 times p. So if we divide both sides of this equation by 32, we get 36 divided by 32, which we can take a 4 out of both those. That would be 9/8. All right, so it would be a distance of 9/8 inches, and in reality, you would probably answer that in your own, actually doing this as a mixed number. So 1 1/8 inches would be an appropriate answer to this question. That's how far from the vertex, how far up that bulb needs to go, so that when the light bounces off from the light bulb to the reflector, it bounces in a straight forward direction. So you can see the road in front of you as you are driving. All right, we'll look at one more little example, and that is that of a suspension bridge. So a suspension bridge, the shape in a suspension bridge, the shape of the suspension cables is parabolic. Okay, we have a cable right there. The bridge shown in the figure has towers that are 600 meters apart, and the lowest point of the cables is 150 meters below the top of the towers. Find the equation of the parabolic part of the cables, placing the origin of the coordinate system as the vertex. Note that this equation is used to find the length of the cable needed in the construction of the bridge. To do that, that's a whole other branch of math. Okay, so we're not going to do that today. All right, but what we are going to do is place the origin right here at the vertex, because that does make it simpler. So if that's an x-axis there, we would have a y-axis coming up through the middle here. Okay, and it says find the equation. So the goal is to find the equation of the parabola that models the shape of that bridge with the cable, the model of the cable, right? So since the vertex is at the origin, we can either use x squared equals 4py or the reverse, but since it opens up, we will use that one. X squared is equal to 4 times p times y. So we need p. But it's actually very easy to find. In fact, it's easier to find 4p than it is to find p, because the focal diameter is the distance from here to here, right? Now, we don't necessarily know that is the focus, but we know that diameter is 600, right? So, and what we can do here is we can plug in a point, right? Just like we did in the last one. We know that when that x is, let's see, it's 150 meters below there, right? So when x is half of the 600 or 300, that distance to the top is 150. So we know that when x is 300, so 300 squared is equal to 150. That equals 4 times p times 150. So if we square 300, we get 90000, so 90,000 is equal to 600 times p. So if we divide both sides of that equation, we'll just do that on the calculator right here. We're going to do 90. I'll scoot this up here so we can see. There we go. So 90,000 divided by 600, we get 150. So P is 150. So it does turn out that that is going through the focus, right? Although that's not necessarily obvious at first glance. But with that, now we can write the equation. So the equation would be in standard form, x squared equals to 4p. But if p is 150, 150 times 4 would be 600 times y. And there you have it.